Thank you. It's a great pleasure to be here. And I didn't know what kind of audience I'd have, so I'm going to be a bit introductory today. My goal is to, at the end, to give an approximate definition of universal mixed elliptic motive. I mean, it'll be more or less complete, except there's lots of things to be explained, and I'll do that in detail in the next lecture. So let me start. So the first thing is history and context, and maybe a lot of people know this, but I thought I'd start here. So very brief comment is, so the 1960s, Grothendieck discussed the theory of pure motives. And so that's an effort to make smooth projective varieties into an abelian category and find a universal cohomology theory. So basically, pure motives over K, and this guy here would be a field. And basically, the objects are varieties, and the morphisms are correspondences, and so on. I think this theory is still not well understood because of all the problems of all the standard conjectures. So basically, objects, smooth projective varieties, and the morphisms are correspondences. So you get more objects because you look at correspondences that are idempotents, and they give you projectors and so on. And so you can break up these varieties. So the second thing is maybe about 1980, there was Bailenson wrote a paper on regulators. And I'm not sure exactly who introduced mixed motives, but the idea appears in this paper. And so, so he defined motivic cohomology. And I'll just recall that in a second, but he defined it. He did an end run about the problem of finding cochains, which was later solved by Vojevodsky. But it turns out, at least for me, it was a very good conceptual way of thinking about this. So how does this work? Of x. And just to be safe, I'll take let's take x to be smooth. But I don't think this is necessary. So, so you have the K-theory of x. So the algebraic K-theory of x, which was defined by Quillen, and you have Adams operations. So and so what do I can't remember how they're written. Yeah. So CP, which take K dot X into itself, and these can be simultaneously diagonalized after tensoring with Q. So you have that K dot X tensor with Q is equal to a direct sum of the, I'll leave when I put this guy here. And so I think this is n greater than or equal to 0, and this is where CP acts by p to the n. So you can break up the K theory here, and basically the projection of this onto this piece is the Chern character. So the Chern, the degree n part of the Chern character is just projection onto this factor here. And this is compatible with maps to all cohomology theories. And so what he did was he defined, I should mention, I don't know how interested you are, but I will I've made notes in this way, and I will put them on the web somewhere. I'll let you know in the next lecture. But anyway, so the motivic cohomology of x with coefficients, say, in Qn is equal to, is defined to be, you look at 2n minus j xn. So this may look odd, so let me take us, say a little word about it. This is a universal cohomology theory for the following reason, because there are maps from K theory. Say if I took K, let me call it Km of x, and I can map it by, say, the degree n part of the Chern character. You think of this as being K upper minus m, so it's in degree minus m, and this will go into any cohomology theory into degree 2n minus m of x with coefficients in Qn. So this is for any theory. So you can put ordinary cohomology, you can put Deligne cohomology, you can put Tull cohomology, and so on. And you always have this map here. And this will always factor through H m x n. But this is just equal to, if I did it right, this is the motivic cohomology in degree 2n minus m of x q n. So it's showing that that this is really the universal cohomology theory. And so if you want to produce, so this is the old-fashioned way, and I guess I'm still old-fashioned, sort of pre-Vojevodsky, is that, you know, there are questions about how do you produce consistent sets of elements, compatible sets of elements in all these different cohomology theories. The idea they all come from the same element of K theory. Okay, and so then the idea was that, again, I didn't run to the library and check this, so I apologize for that. But so this may be a little bit revisionist. I should also point out here, it's not clear that this cohomology theory vanishes in negative degrees. So there's Balance and Soule vanishing conjectures that this guy vanishes in negative degrees. Is that h less than 0 motivic of x qn equals 0, at least when x is smooth. And you can also, later Bloch showed that these pieces here rationally are the same as his higher Chow group. So there are various things that one can do here. That gives you an integral version of this theory. Right, and so another comment is that if x is defined over z, for example, then all of these things should be finite dimensional, and their dimensions of all of these guys are supposed to correspond to the order of vanishing of certain L functions that may not be known to exist. So, so let me give an example. So the first one is, this is really, I'd say, Bloch. Is that x smooth says that H2n motivic. So this is just a restatement of an old result. This is Chow. Because the Chow groups are these graded quotients of K theory in degree 0. So this is Chow group. And then another example is 2. I'd say this is more or less Borel and Balanson. Is that, so let's take F to be a number field. And so you'd like to know what the motivic cohomology of Qn is. So, so let me write it down. So we'll need this later on, and this basically is the ingredient for understanding what mixed Tate motives are, is that the first one is that HJM, I'll just write FQN equals 0, n less than 0. 2 is that H0 equals 0, n not equal to 0, so this is sort of expected. 3, it vanishes Hj, Fqn equals 0 if j is bigger than 1. So the interesting case, and 4, I'll just put H, F, Q of 1 is just F cross tensored with Q. So that leaves the remainder, which is, I'll just write like this, dim H1 F Qn. So this is going to be n bigger than 1 is equal to R1 plus R2 n odd, R2 n even. And here, the degree of F over Q is R1 plus 2R2. And as usual, that's the number of real embeddings, and this is the number of complex conjugate pairs of embeddings, complex embeddings. All right? So, and basically Borel computed the rational K-theory of a ring of integers in a number field by computing group homology, stable cohomology of SLN. And Bailenson interpreted Borel's map. Where did the eraser go? Am I going crazy? Ah, there they are. Okay, good. No, not there. And Bailenson showed, constructed Chern, Bailenson and other people constructed Chern classes. Okay. There's something that okay, so the next part I'm not an expert on. And I think Levine did some as well, is that, and so I think there's another part here is that Bailenson also, I think, conjectured the existence of a category, and so this is what's important for us, of mixed motives. And such that the motivic cohomology of, say, XQN is equal to X in this category of, say, Q, and then you take some motive associated to X, whatever that is, and right. So that motivic cohomology would be an X in some category. And so Vojevodsky and Levine, and this category should be, this guy here should be tannakian. Right, so basically it means it's an abelian category with tensor products and duals and a faithful functor into forgetful functor into, say, finite dimensional vector spaces over Q. So, so Vojevodsky and some due to Deligne, I guess, they constructed a triangulated tensor category with these properties such that So this is incredibly good, but it's not a tannakian category. So right. And I should say something about the objects Q of n, at least in all of these theories. Roughly, these are the Tate motives. These Q of 1 is roughly, I think of it as H1 of G of M. And Q of minus 1 is equal to H1 of the multiplicative group. And then Q of n is equal to Q of 1 tensor n. This is n greater than or equal to 0. Or Q of minus 1 tensor absolute value of n. Right. So that's so I'm old-fashioned, I think, in terms of compatible realizations. So I have a question. Do people take a break after 1 hour, or is this a marathon?
We can take a break after an hour.
Okay. So let me say something about Mixtape motives. So I'd say this is, again, I did not make I did not carefully check the literature here, so I may have the history slightly screwed up. But let's take K to be a number field. And we'll take S contained in its ring of integers. And so the upshot of this work here, Levine first for fields and then Deligne and Goncharov for rings of S integers, is there is a tannakian category of Mixtape motives, I'll call them. Over OKS. And I should say here, these guys have, maybe I'll say a bit more later on, but the fact that you've got maps from K theory, say, into extensions of Hodge structures or Galois modules tells you what the realization of this guy should be. So the Hodge realization of this, it's just the Hodge structure of dimension 1 and type minus n, and the elliptic et al. Is just, it's a one-dimensional Galois representation, so GQ is acting on QL by the nth power of the cyclotomic character. Yeah, so Qn is going to be given by the nth power of the cyclotomic character. All right. Okay, so and so this is only mixed Tate motives. So these are successive extensions of these guys here. So and then you have the property that Hj. Yeah, and I want to underline this here. Yeah. So they have the correct X groups is the point. So the X groups are given by K theory. So, and objects here have a weight filtration. I'm going to start doing something slightly non-standard here. And the weight filtration is by sub-objects of this category, and I'm going to denote it by 0 in the pieces will be called MR of, maybe my object is V, MR of V containing MR plus 1 of V. And so the union should be all of V, and the intersection should be 0. Later on, it'll become clearer, I hope, why I'm using M rather than the usual W, because basically the objects we're going to be dealing with later on in the elliptic case have two weight filtrations. And the thing we normally think of a weight filtration will be denoted by W. And then we'll get a second weight filtration, which will be this one here. So this has the property such that, so I'll use this GRM to R of V is isomorphic to Q of minus R to some power. And GRM odd of V is equal to 0. So mixed Tate motives are of even weight. So if the graded quotients are Tate motives, you don't get anything at odd weights. Let's see. I got lots of experts here and some non-experts. Let me just say, I've got to do this at some point, so I might as well do it now. Quick review of mixed Hodge theory. This is a very quick. So one is, what's a Q Hodge structure? A Q Hodge structure is of weight M. Consists of, the first thing is a finite dimensional Q vector space. And I'll call it VQ. And B, a decreasing filtration F dot of VC. So VC is just the complexification of VQ. And so you'll have VC, and it contains some FPV and so again, the union of these is all of VC and the intersection is 0. And so it has to satisfy VC is the direct sum of HP M minus P, so summing over P, where HPQ is equal to FP intersect F bar Q. So you've got complex conjugation because you've complexified a rational vector space. Right, so and so one very quick example is that 1 QN and 2 this is weight minus 2n, and hm of a smooth projective variety. All right, so now I want to say what so most people, let me just say what so what's a mixed Hodge structure? A Q mixed Hodge structure. So again, V consists of a finite dimensional Q vector space, VQ, B, a filtration of that, so a weight filtration. And here I'm going to use the letter W just to confuse you. So we'll have Wm minus 1. V contains Wm of V. It's defined over Q. And again, intersection 0, the union, the whole thing. And these satisfy each GRWM of V. So this is defined to be Wm of V mod Wm minus 1 of V. With the induced Hodge filtration. Okay, so which means you, for example, restrict to this by intersection, then you project to the quotient, is a Hodge structure of weight m. And so, yeah. Oops, I forgot. C, thank you. A Hodge filtration. I knew I left space at the bottom of that board. Of VC. And Hodge filtrations are decreasing, so this FPV contains FP plus 1 of V. And again, intersecting 0, union, the whole thing. And I got to stress that a little slogan is a mixed Hodge structure is more than the sum of its graded quotients. They're non-trivial extensions, and that's what we're mainly concerned with here. And so a Hodge structure will be a mixed Hodge structure. Again, if you've got a Hodge structure of weight m, you just define Wm minus 1 equals 0, Wm equals V, right? So every Hodge structure is a mixed Hodge structure. All right, so there's something I want to stress here. So there's some important facts. All this you can find in Deline's paper in Publication IHES. Important facts. And so, and to me these are, there are many, but here that GRW dot is exact. The associated gradient of the Hodge filtration is also exact, but, and two, again, all of this, the definition to do Deline and so on, the least trivial thing here is this, Deline, is that the cohomology of every complex algebraic variety has a natural mixed Hodge structure and, you know, compatible with morphisms and so on. Okay, maybe I'll skip that. All right, so, yeah. So let me just do a few simple examples. Whoops. Oh. Okay, let me just think. I just violated the order of my notes, and so now I've got to think about how I want to say something. All right, so what I've got here, let me just try to jump of objects of mixtape motives over Z. So let me say something about this. So again, I'm sure this is well known around here, but let me say it just for completeness. So, so I was saying before, yeah. So when I say realizations, there are various kinds. They come under the name of Betty, sort of Hodge, or maybe I'll put, say, Q de Ram in this case, Hodge, and say elliptic et al. And let me just first of all discuss, and so realization means you've got this abstract motive, and then you can realize it in all these different categories, and these different categories are compatible in strong ways. So V equals Q of 1, I already mentioned before. So Betty, again, apologies for those who already know all this stuff, but right? So it's just equal to H1 of C star. Q is just equal to Q, and I'll think of it times sigma. So here's my copy of C star. Here's my loop sigma. And then let's do Q de Ram. I'm going to do the dual. So if I looked at H1 de Ram of, say, GM over Q, it's just Q times, say, dz over z, if z is the coordinate in GM. So H1 de Ram, okay, we're going to take the dual of that. It's going to be Q times dz over z dual, right? And now you have this an isomorphism, so we can, let's call this will be V Betty equals this. So this is going to be V de Ram equals this. And then you have V Betty tensor C. This is basically the de Ram theorem. V de Ram tensor C. And let's see. So it should be that dz over z check should be equal to should correspond to 2 pi I sigma. Is that right? Or did I put it the wrong way? Did I get that right, or have I got it upside down? Let's see. Yeah, that's right, I think. So, and then this has a Hodge filtration. V de Ram equals F1 V de Ram. And so then you've got Hodge as you put these two together. This guy has a Hodge filtration, and this gives you a Hodge structure of weight minus 2. So sorry, this should be equal to F minus 1 because we're in the dual. Contains F minus 2. Sorry, contains adding 1, F0. Right, and then elliptic et al. So I'm going to put VL is just going to be, I'll take it to be, say, it's equal to pi 1 of, say, GM over Q. Say 1, and this is just going to be isomorphic to the L power roots of, tensor with QL. All right. Okay. So now what about a general V and it's a similar story. So we're going to have V Betty, we're going to have a V de Rham, which is going to have an F dot, and this is a Q. These are defined over Q. And it will, and both of these have a weight filtration. And we're going to have that the Hodge is going to be that V Betty V Betty W dot tensored with C is isomorphic to V de Rham W dot tensored with C. This guy here also has a Hodge filtration, and this together gives us a mixed Hodge structure, whose weight-graded quotients are this is a mixed Hodge structure with weight-graded quotients, say 2n, weight dot of V equal to a direct sum of Q of n's, various Q of n's.
Why did you call it Q de Rham?
I suppose it's wrong. So if you had a different, if you're looking at both,
Because I'm thinking of this is defined over Q. So in the elliptic case, eventually, I'm not going to do it in the beginning. I want to do the Q de Rham case because that's more or less Levin-Rassenay. And Q de Rham gives you splitting. So, I mean, I think even in the theory of mixed Tate motives, the fiber functor is the Q de Rham.
yeah, but two different. So there's the de Rham, which is over the field of definition, and there's canonical fiber functor, which is
Okay, so I mean,
so I was just wondering which one you. So I guess you mean the.
I mean the one over the field of definition.
Okay.
So what should I call it? Just de Rham.
I don't. Yeah, I mean.
See, I think of de Rham as being over C. Sorry. Okay. So, so let's just do a simple example here. So this is an example of a mixed Tate motive. I guess I could have done that there over Q. So let's take V to be equal to H1 of, say, GM with, and say, lambda in K cross minus 1. Mm-hmm. And so we can draw a picture of this guy here. Here is, say, 0. Here's infinity. Here's the sigma in our that we used the generator here. We're going to have a 1 and a lambda, and we'll take a path, say, from here to here. And you can see here that you've got an exact sequence, 0 into H1 GM into V, and then here you get, say, the reduced H0 of 1 and lambda into 0. It's not too hard to imagine that this guy here is Z of 0. So, okay, so here maybe I should take everything's Q coefficients. Right? So, I mean, this example works perfectly fine over Z as well. And so here we still have the form dz over z makes perfect sense. We'll have its dual in here, so this will be in H1 GM 1 lambda, which is the dual of this. So we're going to have the dual class in here, dz over z dual, and here we have sigma. And here we have the path, gamma, which is a lift of the generator 1. And so so to see where the Hodge filtration f minus 1 is spanned by here, say dz over z check, and in say the complex cohomology, and dz over z dual. So to know what the mixed Hodge structure is, as an extension, you have to know where the Hodge filtration is inside this with respect to, say, some integral basis, and it's 2 pi I sigma plus log lambda. So this is really just the integral from 1 to lambda of dz over z times gamma. And so the exact branch of this depends on the gamma you choose, but f minus 1 is determined by, so yeah, gamma is well defined mod z times sigma. And so it's just defined by lambda in c mod 2 pi I z, the ambiguity here or here, whatever. And this just maps by the exponential map into c star, by log lambda. And so this it really corresponds to lambda in c star. And if you think about it, this is actually x1 Hodge. Yeah, I've ended up doing this integrally, so that sequence there made perfectly sense over z. So this is an example of a non-trivial extension, and you can see we're getting, maybe I should have said here, K is contained inside C, right? So, it'll actually be in K cross. The extension is good enough to recover the point, right? All right, so let's look at a much less trivial example. Okay, so 2, I'll do the details actually in the elliptic case, but details of various things, like the definitions and so on. This is due to Deligne and Goncharov. And so let's look at, so we can look at P1 minus 0, 1, and infinity over Z. And we have to make sense of this, but we can talk about, let's let pi be equal to, say, I'll just call pi unipotent equal to pi 1 of P1 minus 0, 1, and infinity, say x at first, take unipotently completed. And I'll define, maybe I'll say a few words now about what this means. Right. And so we'll take, let's just take an x to be an element of q minus q cross minus 1. You know, for some of this, I can just take it to be any complex point of this. And so let's first of all just think of this as the pi 1 in the complex case. So I'll give you a brief explanation. So if I have a group, so what's unipotent completion? I'll do it later, but here's the quickest definition. So I have a group gamma is, say, a discrete group. And I can look at a category C. Let's call it, say, I'm going to say C gamma is just equal to the category of unipotent representations of gamma. So this is a tannakian category. So say over F. So this is a field of characteristic 0. And so this is tannakian. And so you've got a map from C gamma into a forgetful functor into vector spaces over K, and you can just, so what's pi 1, what's gamma, the unipotent completion of gamma over F is just equal to the fundamental group of C gamma with respect to omega. That's the quickest and most abstract way to say it. I'll say it in a concrete way here.
You wrote K.
Sorry?
You have a little K, a vector K. You're walking over F.
Vectors over F, right? So it's just the automorphisms of this fiber functor that are compatible with tensor products. Or I can do it in, here's the most banal way I know how to do it. I just look at all representations of gamma into a unipotent group. So this is so unipotent over F. And I look at, so this is rho. And now you can look at the Zariski closure of the image. That's also a, this is a Zariski dense representation. And now I just look at the inverse limit over all rho that are Zariski dense of the U rho. And this is going to be equal to gamma unipotent completion. And in this case here, if you take a, I'll do this in more detail later on. But so this, for a start, is infinite dimensional. Here, the Lie algebra in this case of pi 1 unipotent is isomorphic to a free Lie algebra on two generators, x0 and x1, and then you have to complete it. So you take Lie power series, and this thing sits inside, say, Q power series in non-commuting. These are non-commuting indeterminants. Right? So we've got power series, and all right. So Delina and Goncharov says that the Lie algebra of pi unipotent is a pro-object of, say, Mixtape motives over Q. In fact, it will, in general, not be, well, it won't, unless we choose the base point carefully, which is what I want to discuss now, it won't be a Mixtape motive over Z. So, all right. So, not a Mixtape motive over Z. So, and because I want to say that why is this the case, if we look at P1 over Z, and we take some X here, so we map this down to spec Z, and now you've got some point here, X. If you look at the picture here, here's spec Z, and you've got 0, 1, and infinity. Every such finite base point will intersect, be 0, 1, or infinity at some places. So if you think about it, if you try to compute the pi 1 here at, say, this prime here, the base point has become 1. It's run off the edge of the variety. So pi 1 with that base point doesn't make sense. So what we're forced to do here, or what Deligne was forced to do, is introduce tangential base points. And let me just be very brief here. So if I take a Riemann surface, you can do this in higher dimensions, but it's easiest for curves. So if I take some Riemann surface and say I've removed some points here, and suppose I want to, so I can use a tangent vector, say, at one of the missing points. So my x is going to be some x bar minus some finite set. This is, say, finite. And I'm going to take S in S and say V inside the tangent space at S of x bar and V not equal to 0. So here's my V right here. What do I mean by pi 1 with this tangent vector? I take paths that leave here with this velocity vector, travel around. So between 0 and 1, the path never leaves x. And then it can return here with negative that tangent vector. You take those guys mod homotopy. That's definition 1. A way I prefer, in fact, I think it's conceptually nice, is or. So you, what you can do is this. Let's take x hat to be equal to the real oriented blowup. So I'll write the real oriented blowup of x at, what did I call it, S. So that means here's the point S here. I replace that with all the different directions I can leave this point. Right, so when I blow up, this becomes a circle. So I've now got a bordered Riemann surface here. So, so the boundary of x hat is equal to S1, which is equal to the tangent space of S at x bar minus 0 mod R plus cross. And now, so when I do that, the picture up here, I would have replaced this by a circle. Everything else is the same. Okay, still got my missing points. And now this tangent vector determines a point here, which I'll call, say, brackets V. And you can define the fundamental group with this tangent vector as base points as being pi 1. So pi 1 of x with base point V, you can define to be pi 1 of this blowup, this oriented blowup at S of x bar minus S, comma V. Right? And that's clearly the same as the usual topological fundamental group. And while I'm here, let me mention that sometimes we're going to have a variation of Hodge structure over such a curve, and we want to be able to talk about the fiber over this base point. It's going to be a limit mixed Hodge structure. So, right, so let's. Okay. So here, what you can do is, so we have P1, and we want to find a base point that is non-zero mod P for every P. So we're going to look at P1 minus 0, 1, and infinity. And there's a coordinate here that is 0 at 0, 1 at 1, and infinity at infinity. And let's let that coordinate be z. And we're going to take d dz, and we're going to take this guy here. It'll be an element, say, of the tangent space at 0 of P1. Right? And that's non-zero, visibly non-zero at every prime. And if we take, so the theorem of Deligne and Goncharov is that pi 1 unipotent of P1 minus 0, 1, and infinity d dz This is also commonly written as 0, 1. ddz is a pro-object of mixtape motives over Z. And so, so there's some remarks in order. So this is an overview at the moment. So remarks are the Hodge periods. One is that the periods of the mixed Hodge structure, so on the Hodge realization, so this is an easy kind of limit mixed Hodge structure here. So on the Hodge realization are multi-zeta values. So zeta of n1, nr, this is something like the sum 1 over k1 to the n1, k to the nr, and I think I need nr bigger than 1, and 0 less than k1 less than. Right. So these are the standard multi-zetas, perhaps written backwards. Yeah, let me finish this remark and then we can take a break. And then the second remark I want to make is that, yeah, let me just stop here. Right, so I was making remarks. There's a few important remarks I want to make. So the second one is, well, we know that MTM, I'm just going to use this for MTMZ, mixtape motives over Z. So this is tannakian. That means it's the category of representations of some pro-algebraic group. And I'll give a brief explanation of what this looks like. So we'll have pi 1. So it's the category of representations of some group. This is a pro-algebraic group. Pi 1, I'll just write as pi 1 of MTM, and I'll be vague about the fiber functor, but it's the common one is the de Rham fiber functor. But so what you want to think about is there's also, you could look at the category of, say, split mixtape motives over Z, right? So what would these be? These, what do I mean by split? It's a direct sum of, say, QMs to some power nm, and you would sum over m. So there's no extension data, just a semi-simple thing. So what would the fundamental group of this category be? It's just the category pi 1 of this category is just equal to GM. Right? You just need to know the weight of a mixtate motive. So QM, so how does GM act on QM? It just acts by the mth power of the standard character of the defining character. I don't know how to say that. Right? So GM, say, if Q sits inside Q cross, and you just take the mth power of that. And that representation tells you what QM is. And so this is a subcategory. So if you think about representations, things go in the opposite way. So we're going to get a map to GM. Right? And so if we had a representation of this that factored through this, it'd be completely split. And the kernel, again, you can think about this, is I I like to call it K. I'm sure Francis has a different notation. But so this guy here is pro-unipotent. And so, and it's telling us about, it governs extensions. So let's just do a little calculation here. So let's try to compute what it is. I mean, I could just write it down, but it's a good exercise because we need it in the elliptic case. So we know that x in mixtape motives, xj of, say, q by qn. So yeah, we'll compute this. And so this is something I think was done long ago by the likes of Deligne and Balanson. They thought about what this should be. So, but this should be, so X in the category of representations of a pro-algebraic group is given by group cohomology. You can define it for pro-algebraic groups. And we're going to take pi1 of MTM, say with coefficients in Qn. And now, if you look at the spectral sequence for this group extension, you'll actually see that this is H0 of GM, Hj of K, tensor Qn. And why is that? Because GM is reductive, right? So every representation splits, so there's no higher Hj. You only get an H0. This is because GM is reductive. And now you look at this here, and strictly speaking, I should be dealing with you. So this is going to be H. Now, if you have a pro-unipotent group, its cohomology is the same as that of its Lie algebra. And so now we're going to tensor this with Qn. And now we're going to take invariance. Right? That's what H0 means. So right. And so what we know is, what do we know over here? We know this is equal to 0 if j is bigger than 1. Right? So this implies that Hj of k equals 0, j bigger than 1, right? Because, and that implies, I can give you references for this. This is all very easy stuff. This implies that k is free. I should say, strictly speaking, it's the completion of a free Lie algebra, right? But it's, and you can work here, because of the exactness of G, the exactness of the weight-graded quotients, you can work here with everything, and then you actually work with the graded Lie algebra here. So the first thing we know is k is free, and then to know what k is, we need to calculate the generators. And so, so k, so this is Lie defined to be Lie of k, is topologically generated by, well, it'll be the duals of, it's going to be okay, but this, how do we know what this is here? Well, whoops, sorry. Yeah. I want to take GM and dual. Anyway, so basically we want to pick up the generators because they're telling us about the one extensions. And we know for Z, we know that X 1 of, say, q by q of n in mixed Tate motives over Z. Remember, this is given by the K theory. This is equal to q for n odd and bigger than 1. And it's equal to 0 for n even. And if you think about this for a second, what this tells you, this implies that K is isomorphic to, though not naturally. You look at this statement here. So,
0 to n equals 1.
sorry?
There's the case n equals 1.
But okay, we're over z. Okay, so what happens with n equals 1? It's 0, n equals 1, because I guess I did it for a field before. Maybe I should have done it for the integers. It's because k1 of z is equal to the units in z is plus or minus 1. When I tensor with q, I get nothing. So this is isomorphic, though not naturally, to a free Lie algebra, the completion of a free Lie algebra with one generator for every odd integer greater than or equal to 3. And so this is quite a famous Lie algebra through the work of various people, including Francis. And I should also say this extension up here is split. There's various reasons. I mean, basically, Levy's theorem implies that this is splitting here. But also, this comes from GRW dot, or there's various ways to construct a splitting here. And so that means this Lie algebra has a GM action that sort of splits the weight filtration here. We can think of this as the completion of a graded Lie algebra. And yeah, and how does GM act? So to get the semi-direct product, how does GM act? So GM acts on Z 2n plus 1 by the 2n plus first power of the defining character. Mm-hmm. So that tells us how GM acts here. So it tells us what this fundamental group is. It's a semi-direct product of GM in this group. And I've just told you how the group acts on the Lie algebra. I mean, that's...
So your defining character is the actual Q of 1, not Q of 9.
yes, it's Q of 1. And if you asked me to put a GM to give you the weight, I would do what I do with Makoto and put a minus 2 there.
Right, okay. So these are positive weights.
Sorry?
That's a positive weight.
Yeah, this is the 2n plus first power of the standard representation of GM. Right. Right. Okay, so the next remark, I should say here, so we now understand pi 1 of MTM is isomorphic to GM, semi-direct product. We can think of it like this, Z3, Z5. Right, so by this I just mean the pro-unipotent group with this as its Lie algebra. And so I think it's the third remark is that so we know that pi 1 minus 0, 1, and infinity. So if we look at pi 1 unipotent of this guy here with the base point, I'll write ddz, is a pro-object. And so more accurately, I should say that the coordinate ring of this is an in-object of mixed Tate motives over Z. And so therefore, it's a representation of this group. So pi 1 of MTM acts on it. And now you could say, how rich is this as a mixtate motive, how representative is it? It could be really boring. It could be completely split. No interesting extensions, or it could have some. So there's the theorem of Francis Brown. I won't ask you to stand. It's that this action is faithful. So the importance of this result is it's telling you that you see everything you want to see. You can construct all of these mixtate motives over Z inside this unipotent fundamental group. And we'd like to have something like that in the elliptic case. We don't, not yet. But that's sort of that's the direction I want to go. And so I should say a corollary, and so this was an open problem. It says the periods of every object of MTMZ are multi-zetas. Right? Because this is basically saying that the subquotients of this guy here generate this category. And so their period, yeah. Sorry?
The periods of MTMZ are multi-zetas along with all the...
Oh, thank you. N 2 pi I. So there's another point I want to make here. So I think of this stuff in terms of moduli spaces of curves. So let me fix some notation. So let's just let M, and I'll say more about this in the elliptic case in the next lecture, but let's let Mg n plus R be the moduli stack of, so here we are going to require that 2G minus 2 plus R plus N. So R and N are in Z greater than or equal to 0. And I put an arrow over this. This is the moduli stack of, and I'll just draw a picture. I take a smooth projective curve of genus G. I'll have n points. So I'll have something like x1 down to xn. And then at r other points, so here I'll have tangent vectors, non-zero tangent vectors, v1 up to vr. So it's a curve plus n points plus r tangent vectors. Whoops. Maybe I'll being inconsistent about how I do this. And every Vj is not equal to 0, and they lie, the points where they're anchored are distinct from all of these guys. So again, we're only going to need this with a few small numbers, but I thought I'd throw this in. I spent a chunk of my life thinking about these guys. So these guys are defined over Z. And so the way I like to think of this is that the genus, so MTM Z is sort of, it's closely related to sort of the MZ n plus R story. And to bring this home a little bit, P1 minus 0, 1, and infinity is equal to M 0, 4. So the next, so basically, yeah, it's genus 0. I mean, there are other things that somehow aren't genus 0, but and so the next step is the elliptic. And I claim to understand all of these higher genus ones, and I may say something about this at the very end. You only need to know genus 0 and 1. It goes back to an old result of John Harrer. It's been elaborated on by various people. So let me start talking about the elliptic case. So there's what I'll call classical, and I'm not sure who's worked on this. Goncharov certainly worked on it. And so you'd like to look at motives that come from an elliptic curve. And the key thing is you start out with an elliptic curve, and to it you would associate a motive, say, H1 of E, in maybe the sense of Grothendieck, that would represent, say, the first cohomology. So let me talk about what this will be. So let's just say, let's suppose that we've got that E is defined over Q, and it has, say, equation. We can always write it in the form y squared equals 4x cubed minus ux minus v. So u, v are in Q. And we have d, which I'll denote as, is defined to be, say, u cubed minus 27 v squared, which is up to a factor of 4 the discriminant of this polynomial. We want this to be not equal to 0. So let's talk about what I'll call it H1 of E. What is it? And I'll talk about just the various realizations. So Betty is, of course, it's just going to be H1 of E analytic, say Q. Let's talk about, I'll still call it Q Durham, or Durham. And so it's, I'll call it, let's just call this H. I'll call it H Betty, H Durham. So you could write the cohomology. The abelian differential here is dx over y is an abelian differential. And you can also span the cohomology with a differential of the second kind, which is x dx over y. So this is of the second kind. It still has a pole, but all the residues are 0, so it gives you a well-defined cohomology class. And even though everything here is holomorphic, this is the this is F1. So this is the abelian differential. And now, so if you take H Betty tensored with C, it's isomorphic to H Durham tensored with C, and this gives you a Hodge structure. Here's the Q structure, the underlying rational vector space, and this gives you the Hodge filtration with F dot. So this is Hodge. This is a Hodge structure. So you can write it as So H01 is not necessarily spanned by that guy there. Right, so let's look at the elliptic. And we have that the Galois group, say, of Q bar over Q acts on, you can look at, say, the L to the n torsion, and this guy here. And so this guy will be isomorphic, or essentially equal to, I guess, the L to the n torsion of the complex points of the curve. And that's just going to be H1 of the complex analytic curve with Z mod L to the n coefficients. So so pi 1 tau of E over Q bar 0, it's just going to be the inverse limit of these guys here. So it's equal to the inverse limit of these guys here. So it's equal to the inverse limit of these guys here, H1. So this is stuff that follows from fancy machinery, but here it's pretty basic. And so this is just isomorphic to H1E. Okay. All right. So right. So the cohomology, if we want first cohomology, H1 of E, say a tau, so with QL coefficients, is going to be isomorphic to Hom of this guy here. Into QL of minus 1. Okay. Sorry? Sorry. Hold it. What? Ah, yes, sorry. This will be the pro L part. So maybe I should just put tensor with ZL. Yeah. So this is the pro L completion of it. This is abelian, so we can split it as. All right. And so we have, and then all of this gives us a Galois action here, GQ. So that's this guy here. And so what should we mean by mixed elliptic motive? So are, say, iterated extensions of symmetric powers. So we're going to take, say, SNH, Tate twists of symmetric powers. And by this I mean the nth symmetric power of H tensored with Q of R. And now, so the category of mixed elliptic motives, as maybe E, should depend heavily on what the curve is. For example, if it has complex multiplication, you will get a lot more algebraic cycles, for example. And so I don't know much about this, but what I want to do is look at the universal case. So what I would like to do is just now give you an overview I mean, it's reasonably complete. If I try to dot every I and cross every T, it'll take a long time. It won't be clear what's going on. So, and I should say here, most of this is joint with Makoto Matsumoto. Joint with some are joint with some other people, and some's joint with myself. Right. So, so what's the idea? So I want so these are elliptic motives. Defined. This is a vague statement for all elliptic curves. So what should that mean? So what we're going to do here is, so more precisely, there are motives associated to the universal elliptic curve. So, and I'll make a comment here. So, K-theory, as I understand it, K-theory is an absolute theory. You can't look at, schemes over something or other. It's an absolute theory, and so I think the theory of motives. Maybe there's some version, relative version, but I think most of it's just absolute. Is that correct? That's what. That's what I. But this is a relative theory. We want to look at this guy over this. And so what we're going to do, so let's give this a name. So we're going, what's the analog of the H over there? We're going to set H. So I use this black bold for local systems. It's equal to R1 F lower star of Q. And again, to be absolutely precise, I have to explain what this means in all these different categories. So it has to be suitably interpreted.
So here you don't take any level structure, so you work.
Sorry?
You don't take any level structure, so you work really with the stacks.
No, I mean, so if you go back to the case of mixed Tate motives, I mean, the ones we understand are the ones where we're just working over Z, right? The analog, I think, of a level might be to work with rings of integers in some other number field, right? So the one that you can define it for having levels, and you can define it over bigger rings, but it's going to be harder, and this is like the first case, at least I think, that should be attacked. We'll see. I mean, curious to hear your reaction. I mean, it certainly would work with levels, but we'll see. I mean, the general setup will. Okay, so what is this? This is the local system. Over, say, M11, whose fiber over the moduli point of an elliptic curve is simply, it's just going to be H1 of EQ, right? But again, the approach I'm going to take here is that this is all, I'm going to look at compatible realizations. And so then, although it's going to turn out that we actually get actual motives, but that's through some strange fluke. And
So before you started, you were looking at homology. For the Tate motive, you were thinking about homology now.
okay, there's always a. Okay, I go backward and forward on this. If I wanted H lower one, I'll just take H1, right? So somehow my brain functions better if I put H in weight 1. So this guy here It's a local system of weight 1 in all senses of the word. So for example, if you think of it as a variation of Hodge structure, it's a variation of weight 1. All right, so let's talk about the realizations of H, so we understand it. So, and again, we need to do more detail here because we need to do computations. Yeah, in some sense, so let me say a word about what's M11 analytic. You can view it many ways, but the way that's most convenient here is it's the quotient of the upper half plane by the upper, so this is the upper half plane. And it's really, I'll write that for Orbifold's quotient. So it's Orbifold's quotient. And what that means in practical terms is you're just working on the upper half plane, but SL2Z equivariantly. It's sort of what everybody does in the theory of modular forms. For a base point, I can choose anything. But in the upper half plane here, we have, we can take a strip high enough up. We're going to have some fundamental domain here. Looks like this. The action of SL2Z. We can say take the stuff of imaginary part sufficiently large. And then when we take the quotient by SL2Z, it's just taking the quotient of this by the unipotent subgroup. Well, we'll take that here. And so I'm going to just set D star is basically the quotient of this strip up here, S. It's just 1Z, 0, 1, the quotient of this strip. So it's like M tau bigger than about 1, I guess. And so I'll take Q. This is all very standard, e to the 2 pi I tau. And this disk here, D star, it maps into M11 analytic.
What about the plus or minus?
I want to take this actual disk. I mean, you can take, right. So, yeah, every point in here has stabilizer minus the identity, so I could do something else. But I want a genuine punctured disk. And now, so what can I use for a base point? I can use the base point DDQ for the base point. So my base point is going to be equal to DDQ, and it naturally, if I look at the imaginary axis here, I can think of it as corresponding to this arc here, the imaginary axis. And so I'm going to include this, if you like, into the upper half plane as the imaginary axis. I mean, maybe I'm being a little too fussy here, but I'm usually fussy about base points. But anyway, so you can also use the upper half plane as a base point. What I'm saying, here's a map between these base points. So with this convention, what I'm trying to say here is that if I look at pi 1 of M11 analytic, dq, this is isomorphic to pi 1 of M11 analytic. And we have the projection here from H into M11 analytic. Maybe I'll call this, I don't know. P is maybe bad, but I'll call it P. And this is just SL2Z. And much to the annoyance of algebraists, I use the topological convention that I multiply paths in the topologist's order. Right, so pi 1, with these choices, you can work it all out, is naturally isomorphic to SL2Z. So a local system, so 1 is Betty. So a local system is really given by a representation of pi 1, and H, Betty, just corresponds to the defining representation of SL2Z. It's just a two-dimensional representation. I'll be more precise about this later on. So I'm going to skip Q to RAM. I actually worked it out, but it's actually very interesting. It's more or less done in the work of Levin and Rassenay, although they left quite a chunk out, actually. And I will write it down later on, but I'll skip that. Let me just do Hodge. So what you can do is you can take H Betty, you tensor it with O of M11, analytic. And so this will be, I'll call this H. So this is a vector bundle. So this is a So H is a locally constant sheaf. This is a vector bundle, and it's got a canonical flat connection. And this is and I'll write this down next time, but this is a polarized variation of Hodge structure. This is the most canonical one of all. It's what's called an SL2 orbit. It's locally homogeneous. And I will describe this in complete detail. It's completely elementary. And it's also a good way, if you don't know the theory of, so polarized just refers to the fact that it has an inner product. So that's actually a flat inner product, say from H over E, tensor H over E into, say, Q of -1, right? This is just the cup product. And polarization just means, basically it means that it's an inner product that satisfies the Riemann bilinear relations. I mean, we won't need to lean on that at all, but it's good to know it's there. But in the general theory, you need a polarization. So this is a leaf sheaf, and it's let me just describe it like this. So whose fiber, say E, say where E is defined over Q, is pi 1 of E over Q bar, say 0, tensored with QL of -1. Just what we wrote down before. Like I said, I'll do the Q to RAM theory later on. I should say more about this base point. For lots of reasons, it's convenient to work with the base point I wrote down, DDQ, because right. So let's say more about the base point. So the first thing is that we need a base point that's non-zero at every prime, right? So if we took some, you might think, okay, let's take some E defined over Z or over Q, whatever, in M11, say Q, and now, but there'll be some prime at which this has bad reduction. So, and at that prime, we can no longer use this as a base point because it's no longer in our space. So we're forced to use bad reduction somewhere. have to use base point. And so there's only, various ways to draw this moduli space. You can draw it as this cusp picture out here, where this is basically where infinity goes, and say I and rho being a cubed root of unity. And our Q disk is out here, so this is really the Q disk out here. If we choose DDQ, that works because the Tate curve, so the Tate curve, so you've got E Tate over, say, Z power series in Q. This, if you reduce it mod P everywhere, it's still smooth. And so, the analog of the tangent vector will be to pull it back to, say, Q bar Q1 over N. You pull this back here. So this is going to be our base point, DDQ. And this guy is non-zero at all primes. So this gives a base point which is non-zero at all primes. And so the only two possible base points we can use are plus and minus this guy here. And it's also very natural when you're working in the upper half plane. Like I explained over here, it's more or less topologically using the upper half plane, the projection from the upper half plane to be a base point, and distinguishing the imaginary axis. So I guess it's a few minutes to lunch. So maybe I won't. Let's see what's a sensible place to stop. Yeah, I'm going to make one point here and then stop, because everybody wants to eat. So this is the point that's most confusing. So that's why I'll give it to you right now, so you can be confused for a week, is this. And this is why I have two different notions for weight filtration. So if you have, first of all, this is just some scribble. If you have a variety, say a curve, and you've got a variation of Hodge structure over it. So here it is here. It's a local system. It won't have a fiber over here. And by method, I'll review all this because I expect most people here don't know it. But you have this local system. So for example, this might be our punctured Q disk, and this is our local system H. And if you look at, so the first thing you can do is you can take H tensor O, and you get the flat vector bundle, this guy here. It has a natural extension to the entire disk, which is called Deline's canonical extension. And you get a fiber of that canonical extension over here. And then to every tangent vector here, you get a mixed Hodge structure on this. Even if you started out with a pure Hodge structure, you get a mixed Hodge structure on the fiber of the canonical extension over the origin of the disk. Right? And so what happened, and this is a very elementary calculation I'll do next time, and I'll completely explain it, is what's the limit mixed Hodge structure. So the limit, and I should say also, the mixed Hodge structure depends on the actual tangent vector. If you use different tangent vectors, give different results. So the limit mixed Hodge structure on H over, even though this was pure of weight 1, over DDQ, I'm going to denote it by H. So this is, and I'm going to denote that fiber by H DDQ, actually turns out to be Q plus Q of minus 1. And you go, this is weird because this was pure, the variation H is pure of weight, this is pure of weight 1. Right? So what I want to do is this. I want to define, well, I should say we have weight 0 of H equal to 0 and weight 1 of H equal to H. That's because H was a variation of weight 1, because H1 of an elliptic curve is of weight 1. As H1 of E is of weight 1 in every theory here, every interpretation. But here we're getting something mixed. So we have to give this weight filtration a different name. So this has got weight 2, and this has got weight 0. You should note the average of these is 1. And so we're going to get a weight filtration here. So we also have a weight filtration, which is called the monodromy weight filtration, which is going to be M on H, right, on this guy, on this limit mixed Hodge structure, which is going to be M0 contains M minus 1, which is equal to 0. This is going to be equal to M1, and this is contained in M2 equals H, right? And so you've got two non-zero graded quotients, this one here and this one here, and this is Q of minus 1, and this is Q of 0. Right? And so, and the similar thing applies in Galois theory. If you use this, if you look at the Tate curve, where did I put it? If you look at the Tate curve over this guy, it's H1 splits as Q plus Q of minus 1. Similarly in the Étale picture. And I'll make my final point. I guess I got 1 minute, 40 seconds according to my watch. Whoops. Yeah, so this is a suitable place to stop. So so H d dq is equal to Q plus Q of minus 1 in all realizations. But because it's a direct sum, this is the, or these I should say, these are the realizations of Q plus Q of minus 1, which is a mixed Tate motive. And so this is going to be the starting point, and this is why I was denoting the weight filtration here by m dot. Because, so in a word, universal mixed elliptic motives are going to be extensions of Tate twists of symmetric powers of this variation, whose limit mixed Hodge structure is a mixed Tate motive, is the realization of a mixed Tate motive, and this forces these things to be genuine motives. And it makes it, the story very rigid. And then you can ask, well, perhaps there are no interesting examples. And what I'll explain next time is there are interesting examples. If you look at an elliptic curve and a non-zero tangent vector, you can take the unipotent fundamental group of E minus 0 with, this is, right, so you've got an elliptic curve, you've removed the identity, so it's got a free fundamental group, and you've got this vector here, and this guy here, and you look at the variation of these. Maybe I should put the Lie algebra here. So this gives you a local system actually over M1 vector 1, and this is a universal mixed elliptic motive, and its fiber, its limit mixed Hodge structure, which is the one associated to the Tate curve up there, is a genuine mixed Tate motive. And so I'll try to explain all of that. So we'll stop here. Are there any questions? I should have asked before. No? Okay.